Okay, so the next question that we have on the menu today is asking us how much power must be applied to this object to accelerate it from rest to an angular speed of 3 radians per second in 7.6 seconds about the x-axis. And then it's asking us, I guess, similar questions if we wanted to get it to rotate about the y-axis and about the z-axis. Okay, so this is a very fascinating question. We have pretty much like I don't know if you guys ever did this as young kids, but for me, like in elementary school, there was like times where we had like marshmallows and we put like toothpicks in between them to make like structures like this, kind of like Connects toys. I'm not sure if any of y'all are familiar with that, but it's kind of similar in terms of what this is representing. We have to kind of assume something though. Assume connections are massless. The reason why we need to assume that these connections are massless is because, well, we don't have any masses given associated with them, so we're gonna assume that there's zero. Like normally, like if you do have anything connected between them, it would have mass, and you do need to calculate that. But we're gonna assume that their masses are so little that we can ignore them. Otherwise, this would be impossible unless we're given them. Okay, cool. So it's asking us for the power applied. And let's represent that with the letter P. Seems reasonable, P for power. And how we want to find this is we want to take the torque that is required to get this spin to happen, multiplied by, I'm fairly certain it's the average. Yeah, it is the multiplied by the average angular velocity over the acceleration. So it's going to be torque times the average. So torque applied average angular velocity during acceleration. Okay, so how we want to accomplish this is first let's find out our W or our not our W omega. Don't say W. That's a scary thing. Okay, so let's find our omega average because we're gonna need to find that for for all three, like part A, B, C. They're all gonna need their omega average value, and it's gonna be the same for all of them because of the acceleration. But the torque is gonna be different because torque is dependent on moments of inertia. But we'll get there soon. Okay, so first get omega average, which is needed for all and same for all. Okay, well our average velocity is just you'd calculate the velocity or you calculate the average velocity similar to how you calculate any other averages. So you would do omega average is equal to the starting plus the end angular velocity divided by the time. Okay, so it mentions that it starts at rest, right? So rest means it has a starting angular velocity of 0 plus from rest to an angular speed of 3 radians per second all divided by how many seconds? It's not how many seconds. I'm tripping. That's not it. This is like the divided by 2, right? Because my bad. I was thinking about acceleration over there. Yeah, it's because we're gonna assume that it's like a constant acceleration. acceleration. Okay, so this is a fairly straightforward calculation. So we know that our omega average has to be 1.5 radians per second. That's going to be important. Okay, so let's square that off. Now we need to find torque in x-axis rotation. Okay, so what I mean by x-axis rotation is like if the x-axis was like the axle of our of a wheel, that's what we would be doing. So what we need to do here is we know that torque is going to be equal to the angular acceleration multiplied by the moment of inertia, right? So the torque in the x component, in the about the x-axis rather, is going to be equal to the moment of inertia about the x-axis multiplied by the angular acceleration about the x-axis. But angular acceleration is going to be the same for everyone. Okay, so let's find our angular acceleration first, because that's what is easier. So we know that our moment of inertia, we'll keep that as like that for now. But for our angular acceleration, we know that this has to be the change in velocity with respect to time. So this will be angular final minus angular initial over the time. Okay, and that hopefully is fairly clear on how that corresponds to angular acceleration. Now for the moment of inertia, moment of inertia is like how difficult it is to rotate this stuff, and or this. So you see how if we're rotating about the x-axis, it's really only the 3 kilogram and the 4 kilogram up here that are going to contribute to the to causing difficulty in rotating here. Because if we're going to assume that the 2.5 and the 1.2 down here, if we assume that those are like perfectly on the line of the x-axis and they don't protrude outwards at all, they're not going to cause any increase to the moments of inertia of the system. Okay, so it's only going to be the 3 and the 4 kilograms that are relevant to this, and we know that the equation for moments of inertia is the sum of all masses with multiplied by the distance that they are, the perpendicular distance that they are away from the axis of rotation. Okay, so in this case, we're given it as 0.5 meters. Okay, so we can sub that into here. Oops, it's r squared. My bad. Okay, so we can send that into the equation here. Is equal to the mass times the distance, the perpendicular distance away, multiplied by final minus initial over time. And we know that yeah, we just need to find this and we'll be good. Okay, so when we scroll back up to here, we know that we only have 2 particles or 2 points that are on this system that are relevant to the moment of inertia. In this case, the 3 and the 4 kilogram. So we shall do this. So the 3 kilogram is 0.5 meters away, meters squared, plus we have the 4 kilogram over there, which is also 0.5, whoops, not 0.5 meters squared away. And then our final angular velocity is 3 radians per second minus our initial, which was, well, 0 because we started at rest. And it's all divided by the time that it took us to change that angular velocity, which in this case 7.6 seconds. Okay, so our torque about the x-axis is going to be the results of this calculation. So 3 times 0.25, because 0.25 is 0.5 squared, plus 4 times 0.25 times 3 divided by 7.6 is equal to, my calculation is, yep, 0.6908 Newton meters. Yeah. Okay, but that is not what we need. We need to get the power, right? And the power is just the torque multiplied by the average angular velocity. We know that the average angular velocity is 1.5 meters. So power for the x direction is going to be the torque in the x multiplied by the average angular velocity. So we know the torque is 0.6908 Newton meters multiplied by omega average, which we know is 1.5 radians per second. Okay, so let's multiply them together times 1.5, and I got our power in the x direction is going to be 1.036 watts. Okay, hopefully that's the same calculation we got here. Yeah, just with a little bit of rounding, but yeah, precisely. So that's in the x direction. Now in the y direction, it's going to be quite the same. So let's actually write it out like the full equation like this, and then we can see what we can sub in. That'll be a lot easier. So now the y direction, or the y-axis. So we know that this is going to be equal to the torque in the y multiplied by omega average. And we know that the torque in the y is going to be the moment of inertia in the y multiplied by the angular acceleration multiplied by omega average. These will be the same, as x-axis. All we have now is just we need to look at who is going to have a contribution of inertia to about if we're spinning about the y-axis. So it's going to be the same equation, mr squared, all in brackets, multiplied by angular acceleration and w average. Okay, so let's take a look at our diagram here, and we'll see if we're spinning about the y-axis, kind of like if we're you know, it's like a flag, kind of like a flag. We can see that we have the 4 kilogram, which is we have the 4 kilogram and the 1.2 kilogram that are going to be relevant to this moment of inertia calculation. The other two, since they're on the y-axis directly, they will not contribute to the moment. Okay, so let's write this out. Py, power of y. So our first mass is going to be the 4 kilogram. 4 kilogram multiplied by 0.7 meters, but we got to square the distance, plus our second mass, 1.2 kilograms, multiplied by 0.7 meters squared again. And our calculation for alpha is, what was it? It was 3 over 7.6. So 3 radians per second over 7.6 seconds. And our omega average was 1.5 radians per second. Okay, let's ask our handy dandy calculator to figure this out for us. So we got 4 times 0.7 squared plus 1.2 times 0.7 squared, close that bracket, times 3 over 7.6 times 1.5. So my power in the y direction is hopefully gonna agree with this. Yeah, exactly. So my py calculation is 1.509 watts. Awesome. Now we want to follow a similar procedure for the z direction. Now the z direction, we don't see it on here, but assume a right-hand rule. So z axis assuming right hand rule pointing out of page. Okay, so right hand rule, our pointing index fingers are going to go along the x-axis, our fingers are going to curl, or our palm is going up towards that y direction. Our thumb is telling us where the z direction is, and the z is, well, pointing right at my face. Okay, so it's kind of like, you know, if you're holding your arm out and you're imagining things orbiting around your hand like this. That's pretty much what we want to imagine here. So PZ is going to follow a similar system. So we have to find the torque in the z direction multiplied by our omega average. And we know that our torque in the z direction is going to be equal to our moment of inertia in the z direction multiplied by angular acceleration, which is the same, and multiplied by our angular velocity average, which is the same. And you know, it might look repetitive, but I just want to be 1000% clear that it really is a very similar thing that we're doing over and over again. And we should expect a different result on this. So when we think about, if we're rotating about the z-axis, we know that, in fact, all of these, except for the 2.5, the 2.5 is the only one that's not going to be relevant to the measurement of the moment of inertia about the z-axis, because this is the only one. The 2.5 is the only one. Excuse me. The 2.5 is the only one that is actually physically on the z-axis. So it's only things that are not along the z-axis that are going to be relevant to this, okay? But keep in mind, we're going to need to do a little bit of Pythagoras math to get the 4, but we'll get there when we get there. Okay, so let's write this out in full. Power in the z. We will first need to do, let's first talk about our 3 kilogram one. So that's going to be 3 kilograms multiplied by 0.5 meters squared plus, now this one, we need to be a little bit Pythagoras to find it, because we're looking for the distance from like corner to corner on, oh, you can't see my cursor, like this corner to corner type distance. That's the distance we're looking for this one. Okay, so that one is 4.0 kilograms, 4 kilograms Now, since we're doing like a Pythagoras theorem thing, it's going to be 0.7 squared plus 0.5 squared, all under the root. 0.7 meters squared plus 0.5 meters squared under the root. But that root really is not too relevant because of, we have to square it. But we'll write it out just to be 1000% complete. And then our last weight that's going to be relevant here is going to be the 1.2 kilogram. And that's going to be multiplied by fairly straightforward 0.7 meters squared. And this whole thing is multiplied by, it's going to be the angular acceleration, which is still going to be 3 radians per second over 7.6 seconds, multiplied by 1.5 radians per second. I believe, yep, exactly. Okay, so power about the z-axis to cause this rotation. Let's math this out. So the first term, 3 times 0.5 squared plus, now this is the spicy one, 4 times, in brackets, is going to be 0.7 squared plus 0.5 squared, but we don't need to put that under the root because the square root and the squared neutralize each other. And then we're going to add plus 1.2 times 0.7 squared. This times 3 times 1.5 divide 7.6. And my result for this is 2.54. And hopefully we have a similar calculation here. Oops. Wait a minute. Something in the math is not agreeing with my calculation and the calculation here. 4.0. Okay, so I trust my answer more because I can see in my calculator that everything's lined up. Nothing to be worried about. It's just a minor calculation error. So my results for this power calculation is going to be 2.4, whoops, not 4, 2.545 watts. Okay, the only thing that's concerning is this calculation right here, but otherwise everything appears to be good. Yeah. Awesome. So that concludes this question. Pretty fun. Pretty exciting stuff, if you ask me. For Z-axis.